Today's lesson 13.4, problem solving with trigonometry. This is where the rubber really meets the road with trig and practicality. We'll cover a couple of problems that you might find useful or seemingly useful. Okay, let's start with triangle ABC and side lengths, of course, the opposite, A, B, and C. In trigonometry, we can find the area of a triangle in terms of its side lengths. For our first one, the area of this triangle can be found by taking 1/2 B times C and then multiplying it by the sine of A. The second one is found by taking 1/2 of AC and the sine of B. If you notice between these two, whatever sides I'm multiplying by, we use the sign of the letter that's missing. So BC, we have the sign of A. AC, B is missing, so we use the sign of B. Then for the third one, we have 1/2 AB sine of C. So again, this works for any triangle, not just right triangles, and we'll start with a couple of examples. So in other words, these formulas work if you find the length of any two sides and the included angle. So now we're going to move up here. So just so we can, because any of these formulas can be used if we don't know what they're labeled. So we're going to say that side A is going to be 3.2. And side B is going to be 4.7, and this is going to be side C, so that would make this angle C. So because we have the angle C here and A and B, we are going to use this formula. The first thing we do is substitute everything in. Again, the area is equal to 1/2 times A, which is 3.2, times B, which is 4.7, times the sine of 142 degrees. So at this point, you can either use a calculator or graphing calculator. If you're going to use Desmos, again, remember to come over here and set it to degrees, because we're going to be working on degrees before you start entering anything. Now you can do these a step at a time, multiply this times 1/2, then that product times that, and then that times the sine of 42. If you want to put it all into Desmos at the same time, make sure you know the order of operations, and since this is all multiplication, we can stick it side by side. Again, coming down here and hitting times. Now we got 3.2, and then hit times again. We got 4.7. Hit times again, and now we've got the sine times the sine, so I'm going to pick the sine of 142 degrees, and I hit enter. And again, that's going to be 4.62977, and we're going to round to the nearest tenth. So the area is going to be equal to approximately equal to 4.6 meters squared, and we got that again from our Desmos function of 4.629 rounding to the nearest tenth. Now here's the second example. Sorry, that's number 2. First example up here. And if you notice all these, it's the sides that are next to it and the included angle. Sides that are next to it and the included angle. So we have the sides that are next to it, included angle. We use this formula C, but we could have used this one if we labeled this one A and this one B, or C and this one B. So these are basically the same formulas. It depends on which sides, if they're labeled at all, but it's the same basic formula. You just multiply this and then the included angle. So again, using any one of these, it's going to be, the area is going to be equal to 1/2 times the two sides and the sine of the included angle. So we can put in any formula here. We can label this A and this C, or this A and this B, or this B and this C, and whatever the angles included here, that's going to be the the letter that's missing. So I'm just going to start here by saying, hey, the two sides, so that's 1/2 times 9 times 13 times the sine of the included angle, the one that's in between them. So sine of 57 degrees. So once we have that, then we can just plug that into Desmos. Taking 1/2 again, and we can go back up here and substitute this in here. So we're going to substitute that for 9, take out the 3.2. Substitute that 13, take out the 4.7, and then I'm just going to change the angle here. Instead of 142 degrees, I'm going to hit 57, and now we've got 49.06, and rounding that to the nearest tenth, our area is going to be approximately equal to 49.1 inches squared. Moving down, it's time for your turn. I would like you to try this triangle out. So I'm going to pause it and give some more video time. Okay, we're going to take it in steps. Here's your triangle. Find the area to the nearest tenth. Again, you got two sides and the included angle. Go ahead and get the problem set up, and when you have it set up, go ahead and see if it matches mine before you make your calculations. So 1/2 times the two sides and the sine of the included angle. If you have this set up perfect, head over to Desmos and check your calculations, enter that in, and find the area to the nearest tenth. And we've got 50.3 millimeters squared. Now on to solving right triangles. What I mean by solving a right triangle is we solve the lengths of all the sides and then solve all the measure of all the angles. So we only have two sides here to start. Of course, we have our angle measure here that we know of 90 degrees. That's our only angle measure. And so when we solve this right triangle, we need to find all the lengths, including this one, and all the angle measures. So we just have to find these two angle measures and this side length. Again, this is a wall with a shelf and a brace. So something you might see and have to figure out for some reason, especially in a math class. So let's begin. So the first thing we want to do is find the missing side. And again, Pythagorean theorem, a squared plus b squared equals c squared. Well, we know what the hypotenuse is. That's 9 squared. And we know that one of the sides is 7 squared, but we do not know the other side. And you can list it as b or a. It does not matter which one's b or a at this point, except that this is now labeled. So this is going to be side A. So I messed that up. Stand by one. Glad I caught that error. So the opposite side of the angle A is the unknown side, so that's the a squared, sorry. And then b squared, we know b is 7. So go ahead and solve the Pythagorean theorem. I'm just going to pause the video and solve it out real quick. So we find that, using the Pythagorean theorem, side A over here is approximately equal to 5.7. Again, rounding to the nearest tenth. Now the next thing to do is to find the angle measure of either A or B. Now remember, we have 7 and 9, so we can use that trigonometric ratio. If we try to find B, it's going to be the opposite over the hypotenuse. So we need to use the, which one? Sine or cosine? The sine. And if we're going to use A, we need the adjacent over the hypotenuse. So if we find a measure of angle A, we're going to need to use the cosine. If we start with B, we use the sine because that's the opposite over the hypotenuse. If we want to find angle A first, we do adjacent over the hypotenuse. It really doesn't matter which one we find first. It just matters if we use B, it has to be sine. We use A, cosine, because we are given these two values. So using the cosine, because I'm going to go ahead and solve for A, I use the cosine of A. Then because we're finding the measure of angle A, the measure of angle A is going to be equal to the inverse cosine of that ratio. And using Desmos, plugging the inverse cosine in for this right here, I get 38.9, and rounding it to the nearest degree, the measure of angle A is going to be approximately equal to 39 degrees. Now I could do the same thing if I wanted to try the sine. If I do the sine, I'd have to use angle B now because I've got the opposite. So the sine of angle B equals 7/9. Okay? But if we know this is 39 degrees, all I need to do is add 90 plus 39 degrees to get 129 and subtract that from 180 to find out that the third side is going to be 51 degrees. But that should then say that if I find this angle measure using the sine, that should come up with 51 degrees. Let's go ahead and try it. So we're going to say the measure of angle B is equal to the inverse sine of 7/9. And so the measure of angle B, we're going to say, is approximately equal to 51. But let's do the math real quick here. Inverse sine of 7/9, and absolutely, that's what we get. 51.05 degrees, rounding it to the nearest degree, we get 51. But then again, we already knew that, right? By using the 180 minus the remaining angles. So now it's your turn. Go ahead and pause the video and read this problem about the building casting a shadow, and then it gives us our steps here. Use a trigonometric ratio to find the distance. Use another trigonometric ratio to find the distance df, and then use the fact that the acute angles of a right triangle are complementary and find the measure of angle D. So the first thing it wants us to do here is use a trigonometric ratio to find the distance EF, and that is the height of the building. Well, if we have the measure of angle 27 and we have the opposite and we need to find the adjacent, what trigonometric function gives us opposite over adjacent? That would be the tangent function. So we need to find the tangent, and the tangent we know of 27 degrees. Okay, tangent 27 degrees is equal to the opposite, which is 33, over the adjacent, which is side EF over here. So I'm just going to put segment EF. At that point, we just need to use our algebra. I need to eliminate EF from the denominator, so I multiply both sides by EF, and it becomes EF times the tangent of 27 degrees equals 33. And again, divide both sides by the tangent of 27. Oops, tangent of 27 degrees, sorry. Did not mean to write that small. So now we need to solve. So EF is going to be 33 divided by the tangent of 27 degrees. I'm going to switch over to Desmos here real quick. And putting that into Desmos and order of operations, we know that side EF is approximately equal to 65. Then number 7 says use another trigonometric ratio to find the distance DF. That's actually going to be the hypotenuse. So if we have angle 27 and we know its opposite, which is 33, and we need to find the hypotenuse, which is DF, that's going to be opposite over hypotenuse is going to be using the sine function. And if you notice, it's set up the same way with df in the denominator. So it's going to be end up df's going to be over here. We're going to have df is equal to, if I multiply both sides by df and then divide both sides by the sine of 27, just like I did up here, we're going to end up with 33 divided by the sine of 27 degrees. And that putting it into Desmos is going to give us approximation of 73. So that's going to be df is approximately equal to 73 meters. So now we've solved both sides. Our third one says, use the fact that the acute angles of a right triangle are complementary to find angle D. Well, in order to do that, I know that one side's 90, and we got one side of 27, correct? We add those together, which equals 117. And then 180 degrees minus 117, you can do this on the calculator if you want to, is going to give us 63 degrees. So now we've solved everything that it's asked us to. This last section, which I'm not going to go over, is solving right triangles on a coordinate plane. The only thing you need to use on here is the distance formula to figure out the length of the sides. Once you have those and any of the angle measures, especially you've got a right angle of 90 degrees, but then you can use the trigonometric functions to find one of the missing angles, either sine, cosine, or tangent, depending on what you solve here. So there's only going to be I believe one problem on the worksheet that handles this, so I'm not really going to go over it because you can use anything that we have for the past couple of weeks to, again, figure out and solve this. If you have trouble with that, or any of these on the worksheets, please reach out to me by email and I'd be happy to go over it with you. But this concludes our video at this time. If you need to recheck anything, go back and watch the video or any of the other videos to complete the attached worksheets.